Hello, this is Thomas Holden from tsholden.com. Recently, I've been doing a lot of thinking about navigating a truly three-dimensional space. This is because of the Sea of Memes project by Michael Goodfellow, who is building a game which has all kinds of cool objects, like asteroids and ring ships and generation ships, all orbiting a single planet. The thing about these 3D shapes is that they raise some very basic questions that you usually don't have to ask in video games. For example, which way is down? Normally this is a given. Down is down. But when you're walking around in space, it becomes incredibly important, and it can be quite tricky to figure out. The now classic example of this is Mario Galaxy. Mario could walk around on any number of shapes, and it all worked out like magic. But obviously there's some very serious code running in the background of it all. So I've been rolling the question of how to do this around in my head, and this is what I've got so far. For the purposes of this video, I'm going to be talking in 2D terms and using 2D illustrations. However, the general ideas can be scaled up to 3D without much change in concept. To start with, we have to be able to stand before we can walk. Really, this is where most of the trickiness comes into play. So let's make a simple planet/asteroid to stand on, starting with a simple circle. We can represent the player as a simple blue dot. In a first-person game, like Sea of Memes, this is the head of the avatar, as well as the game camera. Now the body is going to be below the head, towards the planet. Simple enough. But what if we're standing somewhere else? Well, let's put a player on the right side of the planet. Now their body is going to end up hanging below them to the left, from our perspective, towards the center of the planet. Already, we're seeing a simple solution emerge. Just use the middle of the shape that you're using as the center and call it a day. Let's test this by putting another player on here and pointing his body towards the center. Yeah, looks right to me, right? But this is a video game. Video games tend to have some situations that don't conform to reality. For example, a rectangular planet. So we'll put a player on here, point his body, put another one on here, point his body. Yeah, both of those point towards the center and they look right. But we've got a corner case, literally. Put a player at the corner, point his body towards the center of the planet. That doesn't look right. What if we want it to be like this? That looks right. But that doesn't conform to our rule. Let's use another shape that will probably come up in a video game. For example, this semicircle. Common enough shape, right? Now, here's the actual center of that semicircle, if we're counting mass and all that. Put a player on there, point his body towards the center. Alright, that looks okay. Put another player on there, point his body. That looks less right. Something like this would look better. Now, in order to do that, we'd have to move the center to there. That's the visual center, but not the actual center. So, very much breaking the rule that we've been going with. Now, just to drive the point home a little bit more, I'm going to make another shape. This monstrosity of a planet is actually pretty believable in terms of players could make this. So the actual center of that's no good. What about the visual center? Well, that's right there. We put players on there and they start getting pretty confused and alarmed. Generally bad times all the way around. So what we're seeing here is that the player doesn't really want to be standing pointed towards the center of the planet. The player wants to be standing with their feet pointing towards the edge of the planet they're on. They want to be standing perpendicular to the edge. So if you've got a box like this, and we want down to be like this and down to also be like this, we might want to approach the problem by defining some regions. We can define regions by just splitting up along the corners of the shape that we're standing on. Corner here, corner here, corner here, corner here. All it takes is a little bit of high school math to be able to figure out the angles of these and divide the space around the planet into regions. We can test this by putting some bodies on here, and whichever way is down in the region that they're standing in is which way their bodies point. All that said, regional gravity does have its share of problems. Let's create a triangular planet. Here are the lines showing us our regions, and here's the way that gravity points in each region. Now, if the player is standing near one edge like this, and then he takes just a few steps over, he's going to flip over. This is the big difference between regional gravity and point gravity. Point gravity always has smooth transitions. Regional gravity can be very sudden and very disorienting to players. Game developers can compensate for this deficiency by designing levels that have smooth transitions between regions. As an example, let's use our circular planet. Now, in a video game, we would use a series of segments to represent a circular planet, rather than a true circle. The common number of segments would be 12, because it looks okay without wasting resources. 12 sides means 2, 4, 6, 8, 10, 12 different regions have to be defined. As you can guess, the number of regions can exponentially grow as you add segments to your world. This is especially the case once you introduce multiple planets. Let's make 2 simple box planets and project their regions out from their corners. We can use the intersection of our lines to help us figure out the division point between regions. It's worth pointing out that that top point and that bottom point where the regions intersect would be a terrible, terrible place for a player to end up. For the sake of illustration, let's add yet another planet. Again, we're going to use a simple box. Once we start projecting out our lines to create our regions, we can immediately see how complicated this gets. So now let's look at a different approach. We start with a box planet like before, and place our player above it. This time what we do is we create an invisible circle around the player and expand it. Once the circle intersects with the box, we note the intersection. This point marks which direction is down, and therefore which direction our body should point. We can test this method by creating another player to the right of the box planet. We expand the circle from them, mark the intersection, and sure enough, their body is pointing in the correct way. Now we can test our corner case to see if it works correctly. Note that when we mark our intersection, it's exactly where we want it to be. One of the advantages of using this expanding circle, or a sphere in 3D, is that it can handle moving objects. To illustrate this, let's create a circular planet and place the player fairly far away. This means that their expanding circle will end up growing quite large. Once the circle intersects, we orient towards the planet and start falling. But now let's give the planet a moon. Moving the moon along an orbital path, it ends up being closer to the player than the planet. The next time the circle expands, which should be happening several times a second by the way, it'll hit the moon instead of the planet. This new intersection means a new down, which means the player will start falling towards the moon rather than the planet. Let's revisit this planet. Let's scatter some players about at random, expand their circles, mark the intersections, and point them down. All of that looks right. Alright, let's try a more complex shape. When trying players out at different locations, the first 2 don't give us much trouble. The second 2, on the other hand, collide early with the wall. It's easy to imagine a situation where you want this set of collisions leading to this set of downs, but that might not always be the case. The solution is to build the planet out of 2 separate objects. The first object is just like every other planet we've made before. The second, however, is marked as a non-colliding object. This way, when we expand our collision circles, they all collide with the single horizontal edge of the first object. One last test is to throw the player between 2 planets. Since the player and/or planets are likely to be in motion, the odds of them being exactly equidistant to both planets is infinitesimal. Alright, I hope this video has given you guys some ideas of your own. Obviously, there's no one perfect solution to a problem this complex, but there are some advantages and disadvantages to each solution. Feel free to leave a comment below or send me an email at tsholden@tsholden.com. Thanks for watching.